Hey guys, so we are Team 4 and we did the deduplicator. So a deduplicator is a specialized data compression technique for eliminating duplicate copies of repeating data among many files. So the intent of storage-based deduplication techniques is to look at a large volume of data and large sections and identify such sections that are identical in order to only store that copy of that section once. So this is especially useful in the case of data backups, which routinely are performed to protect against data loss because most data in a given backup is going to remain unchanged from the previous backup, and so you don't want to store multiple things many times. So deduplication of two files A and B is illustrated below, which have a large common subsection in orange. The orange subsection, though it appears twice, is only stored once, whereas the purple and green only appear once and are stored once. So we've saved space equivalent to the size of this orange chunk. So how did we implement it? Well, we needed to break the file up into many separate chunks, and in order to do that, we used Rabin-Karp fingerprinting to establish the chunk boundaries. Once we had the MD5 hashes of the established chunks, we stored the hashes in the file chunks into a hash map, with the MD5 hash as the key and the file chunk as the value. Once we had this global data structure, we were able to store the file as an array of MD5 hashes which index into this global hash map. So the crux of our project is really in our chunking strategy. So a naive way to chunk might be to say, let's set the chunk sizes to a fixed number like 8 bytes. So in this case, we find 5 out of 7 chunks are duplicates because the data is properly aligned. But as soon as you have misaligned data, even by a single character insertion, the hashes for each of these chunks would differ completely, and thereby not finding any duplicates even though a majority of the data is shared between the two documents. Given these setbacks, static chunking isn't the right solution for this problem. So what we need is something a little bit more like this. Variable block or dynamic chunking is going to allow us to set the chunk boundaries based on the content of the data rather than just arbitrarily picking a random chunk size and then setting the chunk size to that throughout the file. So as you can see here in this example, the first boundary is actually maintained between 1, 2, and K and L, rather than shifting like in our previous example. In order to achieve this variable chunking strategy, we use something called a rolling hash. So in a rolling hash, a fixed size window is created. In this case, the size is 8. The window is then slid along the data, creating a hash value for every window within the data. If the hash matches some fixed criteria that we decide, let's say that the last 2 digits are EE, then we can set a chunk boundary at that location. Although this algorithm may seem really slow because we have to compute a hash value for every window of some fixed size within the data stream, it's actually really fast if we use a hash function that matches a certain property. What we want to try to do is see what hash function we can use such that the hash of the next window will be some function of the incoming byte and some function of the outgoing byte, because most of this data remains the same. So on our data, we have to establish a window size. So let's say we establish a window size of 3 on this. So to calculate the hash on this window, what we do is we use a large prime. So we take the first value, A, and we multiply it times P, but we multiply it times P to the power of the window size minus 1. So in this case, the window size is 3, so our power for P is going to be 2. And it sort of follows suit. The next one is the window size minus 2, so that's going to be just 1, and then times the character, which is B, plus P of 0 times C. So this is what we establish our hash to be. So now this is useful to us because we can actually calculate the hash value for the next window in a constant number of operations. Now let's see how we would do that. So to start, let's multiply everything times P. Now this portion looks like the beginning of what should be the hash value for the next window. So next, what we're going to do is actually add in the incoming byte. And we're going to subtract this term out, which is the outgoing byte, times prime to the window size. What we're left with is simply p to the power of 2 times b plus p to the power of 1 times c plus p to the power of 0, which is just 1, times d. And this is actually the rolling hash value for the next window, B, C, D. And so all we had to do to get this was multiply everything times p, add the incoming byte d, and then get rid of the highest term, which is prime to the window size times a. And in a constant number of 3 operations, we've essentially managed to find the rolling hash value for the next window. So now we have this ingenious sort of way to calculate the hash for every window in our data stream. So by specifying some criteria, like whether our hash modulo, a number, is equal to 0, can give us some ways to control where the algorithm lays down its boundaries. So once we lay down our chunk boundaries, we take each chunk and run it through an MD5 hash, thereby generating a hash key. At the bottom here, we have a hash map which uses the generated MD5 hash and indexes into a hash table which contains a locker file. Now, a locker file is just the byte array that is the chunk, and also a reference counter to indicate how many different files are pointing to this specific chunk of data. So the next thing to do after we've entered our chunks into the global hash map is to store the hashes that refer to the chunks so that we can reassemble the file later. The MD5 hashes are simply added into an array list, which can be used to index into the hash map and retrieve the chunks that they represent. Because of the way we've implemented our locker, a simple add operation will only take linear time. First, we have to run it through the Raman-Karp hashing algorithm. Because of the fact that it's a rolling hash and has constant operations to calculate each window, it's only going to take linear time to do that. Next, we have to hash each of the chunks with the MD5 hash, which will take constant time for each chunk. After that, these chunks must be added into the global hash map, and then a file array must be created, both of which will take constant time. In order to retrieve a file, we must look at its array list of hashes, and then use the hashes to index into the global hash map of chunks, then reassemble the chunks from there. So this is also linear in the size of the file that we're retrieving. The delete operation would actually be constant time. All we'd have to do is for every hash in the array list of hashes, we would just have to index into the hash map and then decrement the reference counter for each locker file that corresponds to one of the hashes. If the reference count hits 0, then we simply delete that chunk from the hash map. Okay, so here we are. We have an instance of our program running on the left, and we have a simple Python script on the right for data generation. So I'm just going to run this script really quickly, and you'll see once it finishes that in this folder where testfilemaker.py sits, we'll have 10 test files generated. Okay, so we see that in 22 seconds we were able to generate these files. Now, these are just files that are around 10 megabytes and differ by at most 10 character edits. Okay, so the first thing we're going to do is we're going to create a locker. And you'll see that our locker pulled up right here. So next, I'm going to open that same locker we just created. And now I can simply add files. So let's check the file size of our locker real quick. So we see it's only 88 bytes. Now when I go to add a file in, I'm going to go pick the same pick a file from our test files and add it in. So as you see, test 0 just popped up, so we're going to go to locker and check it out. So as we can see, we have a 10.1 megabyte locker, which makes sense. Our file is around 10 megabytes, so this 10 megabyte file just got added in. Now we do the same thing, and let's go add in another piece of data. So now we add in test 1, and we check our locker size again, and it's increased by about 0.3 megabytes. So we added in a 10 megabyte file, but our file locker file only increased by 0.3 megabytes. So it looks like the deduplication was a success. So now in this next example, we actually have a test folder. So I look in here and we have all of our 9 test files just like before. So what we're going to do is actually add the whole directory. So I select the directory and press open. So now it prompts us on whether we'd like to add this directory recursively. So we select yes. It takes some time. And now our test folder is added in. So if we look at the size of our locker, it's actually 19.1 megabytes. So we took a file folder that was 100 megabytes and turned it into about 19. To increase on efficiency, we actually multi-threaded the add directory process. Every file would get its own thread, and that thread would be responsible for adding the chunks of that file into the global hash map.